Good day, class. It's nice to meet with you again. Today we'll be looking at something very, very interesting. How to write the formula of a compound. You'll recall that the last time we met, we considered the periodic table. And in that topic, we also looked into the symbols of some elements. And prior to that, we had also considered the valency of some of these compounds and elements. And today we'll be looking at how to write the formula of a compound. So the objective of today's lesson will be to determine the charge of an ion, still the symbol and the charge of a polyatom, and finally, to write the formula of a compound. You were also familiar with molecules when we treated diatomic and polyatomic molecules. Take, for example, hydrogen, oxygen, and the halogens. All exist as diatomic molecules. Will we also, for the sake of revision, look at some of these symbols that we're already used to. We know the symbol of aluminium, beryllium, boron, down to calcium, gold, and iron. And then on the other column on this table, you can see bromine, nitrogen, chlorine, and all that. These are molecules that have more than one atoms in them. Okay, so first thing we're going to consider today is to look at some common compounds. I would say some common molecules. Okay, if you look at this critically, you will notice that ammonia, the first on the list, the name itself does not suggest the constituent elements, okay, or the constituent atoms that makes up ammonia. Okay, so from the name ammonia, you can't really tell, oh, what can the elements that makes up ammonia be? From the last one, we have water. From the name water, water is also a compound, but from the way the names sound, you can't really decipher or derive what constitutes water, okay, from the name. And then we also have methane, okay, which also have the same issue. So that tells us that not every molecule follows a straight jacket rule when it comes to deriving their formula, okay? But there are some other molecules that we can actually write their formula easily from their name, okay? Before we do that, we have to take note of some of these basic rules, okay? And the first is, when you look at your periodic table, from group 5 to 7, the elements there are typically nonmetals. And now these nonmetals, when they combine with other elements, the ions they form have the suffix IDE, okay? So I'll take, for example, let's start with the group 5. Check your periodic table for group 5. You know the first member there is nitrogen, okay? So for nitrogen, we'll say no, when it's the ion of nitrogen, when it's in a combined state now, will be nitride, okay? So the OGEN have been substituted for IDE. Oxygen, okay, follow the same. Oxygen becomes oxide, okay? And then let's talk about sulfur too. Sulfur automatically becomes what? Sulfide, okay? And then let's pick an halogen. The first one there is fluorine, okay? And fluorine also take the name fluoride ion. So you have to get used to this naming technique. It's very, very important. Okay. And if you would recall, we also made mention of some of the um, nomenclature technique we use for to indicate the number of atom in a compound or the number of ion in a compound. Take, for example, when we hear the word mono, it simply means one. Di means two, okay? And tri means three. Of course, four is tetra, okay? So we use all this to denote or to indicate the number of ions in a particular atom. I mean, a particular compound. So we'll pick other examples on this table, okay, and see how easy it is to write their formulas by just measuring their name. Okay, take for example carbon dioxide. Okay, from the name carbon dioxide, it's simple, it's very easy for us to give a name to it. Okay, and that is from the word carbon. We already know the symbol for carbon is C, and then for oxygen, because we have oxide here, okay, which denotes oxide here denotes oxygen, right? So if oxide denotes oxygen, then we just have to put our O here, okay? And the di here, remember, denotes two, so we'll put two. So carbon dioxide, meaning carbon bonded to two oxide ion, okay? The di means two. The same principle applies to your monoxide, okay? Carbon monoxide, okay? Here in this case, we have carbon and then we have oxygen. The mono here, as you can see, indicates one here. So there's no need adding any number there to indicate it is two, okay? So mono means just carbon bonded to one oxide ion, okay? And that is what gives us the formula CO for carbon monoxide, and then CO2 for carbon dioxide, okay? So I'll just give you a minute to quickly tell me what the name nitrogen dioxide. Good. You have nitrogen dioxide. What would the formula be? Okay. So I want someone to try that out quickly and get back to us. Wow, that's great. That's perfect. So looking at this, you notice what you did is simple. You said the symbol for nitrogen is N, and we have oxide, of course, which is O, and then the di there suggests we have two. Okay, so and then you just include your two. That's perfect. Bravo. That's good. That's good. That's good. So that is how to give names to um, some of these molecules. So I mean, write the formula rather to some of these molecules. So it's pretty easy. Okay. So we now move on to ionic compounds. Before we do that, it's good for us to know how to generate charges, okay? Charges of, what about ionic compounds? We mean compounds that have both metals and what? Combining with a non-metal, okay? If you check the examples we've treated so far here, we were treating molecules, and molecules are just non-metals combining with themselves, okay? But now we want to look into metals combining with what? Non-metals. When this occur, you get what we call ionic compound, okay? So we'll be looking at the ionic compounds now, okay? So how do we get the charge of metals first? Your metals, as we learned the last time, or treated periodic table, we learned that your group 1, group 2, group 3 are your main metals, okay? And hence, their charge follows that pattern. That is group 1 plus 1, group 2 plus 2, group 3 plus 3, okay? I will just pick 2 examples, okay? Let's say calcium, okay? We know calcium has atomic number 20, okay? We have aluminium, okay? We have aluminium, okay, which has atomic number of 13. So when you're writing the electron configuration showing their energy levels, the first energy level will take 2 for calcium, followed by 8, and then the third one 8, and then the last will be what? 2. So for calcium to achieve stability, it needs to give out 2. Remember, metals generally lose electrons to achieve stability, while non-metals, on the other hand, gain electrons to achieve stability. So when it loses 2, it implies that your calcium becomes Ca2+. This is the charge of calcium ion, okay? Is Ca2+. Okay, this calcium ion. For aluminium, we follow the same rule to generate the charge. So the first energy level will take 2, and then second 8, and then 3. Okay, of course, it's a metal, hence it's going to lose this 3 to achieve stability. Remember what we said initially? For atoms to achieve stability, they have to get the noble gas electron configuration. Okay, so that's why we make sure they end at 8 here. So 3, meaning aluminium ion, will be expressed in this form. Okay, 3 indicating 3 outer electron, and also group 3. So for the sake of speed, all you need to do is, when you hear the name of the ionic compound, just pick your periodic table. Oh, where is this metal located? If it's located in group 1, then the charge of the ion of that metal will be +1. If it's in group 2, then the charge of that metal will be +2. If the metal is in group 3, then the charge will be what? 3+. So that is for metals. Now for non-metal, take for example, we have nitrogen and sulfur. Okay, nitrogen and sulfur. Okay, nitrogen is 7, sulfur is 16. Okay, so how do we determine their charge? Okay, the first energy level here will take 2, and the second energy level will take the remainder 5. And then for sulfur, we have 2, 8, and then 6 for 16. So now, for non-metals don't lose electrons, rather they gain electrons, okay? How many electrons will nitrogen gain to achieve the noble gas configuration to become 8? Remember, end with 5 here, okay? So it will need 3 electrons to make it up to 8. So that is a minus, okay? We indicate that as minus because it's gaining electron, okay? Remember, the charge of electrons is negative, okay? So when you're gaining electron, you become negatively charged, okay? So that is why non-metals always have a negative charge. Okay, so nitrogen, we need 3. So this rule applies to all the elements in group 5. That's the implication. So that means the elements in group 5, I mean the main group 5, will have a charge of 3 minus. So if you check the group 5, you have the main element there, we have nitrogen, we have phosphorus. So phosphorus 2 will be 3 minus. That is the implication. Okay, and then for group 6, here for sulfur ends at 6. That means it's short of 2 electrons to make it up to 8, where it can achieve stability. So it will need to gain 2 electrons. So that means my sulfur, which is S, will be what? 2 minus. So I used to tell my students that these things, when you are in a typical exam condition, all you need to do is just use your periodic table. Okay, you don't need to show all this. Okay, just use your periodic table. You don't need to show all this. If the element is in group 1, of course, the charge will be +1, group 2, +2, group 3, +3. But if the element is now in group 5, that's after your group 4, from 5 -3, of course, you need 3 to make 5, 8. Group 6, you need 2 to make it 8, so the charge will be 2 minus. And then group 7 will be what? -1 or 1 minus, because you need just 1 to make 7, 8. So with the use of a periodic table, you don't have problem at all. It makes you work very, very fast and smart. Okay, so how do we give name to compounds, to some of these ionic compounds? Take, for example, you have calcium. No, let's start with aluminum. Aluminum nitride. Okay, so when you have aluminum nitride, what will the formula be? Simple. Aluminum, the symbol is Al. Okay, and then nitride suggests we have nitrogen, isn't it? Okay, so what is the charge for nitrogen? So charge for nitrogen, nitrogen is in group 5. That means the charge will be 3 minus. Okay, as earlier established. Aluminium is in group 3 on your periodic table. Okay, which means the charge is 3 plus. Okay, so that brings us to the rule of naming. Of writing the formula. The charges, the rule is the charges must sum up to 0. And you know, when you have +3 and -3, you automatically get what? 0. So that brings us to this as the formula for aluminum nitride, ALN. Okay, because when you add up the charges, you get 0. Okay, so that is the formula. What about where we have things like calcium nitride? When you have calcium nitride, how do we write the formula for calcium nitride? We already established the fact that calcium has a symbol of Ca, and then your nitride is N. Now I want you to look closely to this. Calcium is in group 2, which suggests that the charge will be 2 plus. Okay, as your metal is 2 plus. Okay, and then my nitrogen is 3 minus, as we have it up there. It's in group 5. Now, there's a problem here. There's no way +2 and -3 will give us 0. Okay, when you come across problems like this, where the net charge, the sum of the charges, does not give 0, the fastest way to solve the problem is to crisscross. What do I mean by crisscross? You take the charge of nitrogen, you multiply it with calcium, okay, and take that of calcium and multiply it with what? Nitrogen, just like an exchange. Okay, and when you do that, the 3 for nitrogen goes to calcium, so you now have 3 calcium atom and what? 2 nitrogen. Okay? So the implication of this is that when you do this, you now get 0 eventually. How do we know we have 0? Remember, calcium was 2 plus. 2 times 3. 2 times 3 for calcium, of course, gives 6 plus, right? And then nitrogen is minus 3, was not minus 3 before. Okay, so your minus 3 times 2, okay, so we have 2 nitrogen here, you get minus 6. And that will sum up to what? 0. So that is why the formula for calcium nitride is Ca3N2, not as straightforward as aluminum nitride. Okay, so before we end the class today, I want you to try giving the name. Let someone try sodium. I need the formula for sodium oxide. Okay, sodium oxide, using the same principle that we've adopted. Oh, that is correct. That is great. That is great. So that means you're doing well. That means you're saying sodium with the symbol Na, and then oxide is oxygen. Wow, that's good. And then oxygen is in group 6, which means the charge is 2 minus, and sodium is in group 1, which means the charge is plus 1. Ah, wonderful. Okay, and then you crisscrossed because when you sum up these charges, they don't amount to 0. So we have to crisscross the 2 for um, oxygen goes to sodium. So sodium becomes Na2, and then the 1 for sodium goes to oxygen, and then oxygen stand alone. So this is the formula for sodium oxide. Oh, that's good. That's good. So we'll stop here today. When we meet next week, we'll be looking at how to name ionic compounds with polyatoms or radicals. Okay? That's great. That's great. So at this juncture, I would like to say bye till we meet next time. Okay?